Once we determine the Lewis structure of a molecule, we can also determine the shape of the molecule using valence shell electron pair repulsion theory, or VSEPR, also called VSEPR. In this model, the structure around a given atom is determined by minimizing repulsions between electron pairs. In other words, electrons want to get as far apart from each other as possible. In organic chemistry, because we are dealing with elements mostly in the second row of the periodic table, we only need to review a few types of VSEPR geometry. First, let's define some terminology that I will use. An electron domain is a region of space where electrons are. A lone pair counts as one electron domain. A single bond counts as one electron domain. A double bond or triple bond also counts as one electron domain. For example, this nitrogen has 3 domains. The lone pair is 1, the single bond is the second, and the double bond is the third. Next, let's differentiate between electron domain geometry and molecular geometry. Electron domain geometry depends only on the number of electron domains around the atom that we are considering. This is what we care about in organic chemistry. Molecular geometry depends on whether those electron domains are lone pairs or not. We generally don't care about this in organic chemistry. Let's look at a few examples so that you can understand what I am talking about. We'll start with CH4, methane. Here's the Lewis structure. The C has 4 electron domains surrounding it, each of the single bonds. You may remember that the geometry for an atom with 4 groups is tetrahedral. This is both the electron domain geometry and the molecular geometry. We can draw a fake 3D picture like this. The wedge that's colored in shows a bond sticking out of the page in front. This dashed line shows a bond that is going back behind the page. The straight lines are in the plane of the page. Build a model to remember what this looks like. The angle between any 2 CH bonds is 109.5 degrees. Ammonia, NH3, and water, H2O, both also have 4 electron domains around the central atom. This means that their electron domain geometry is also tetrahedral. You may remember that ammonia has a molecular geometry called trigonal pyramidal because it has 1 lone pair and 3 bonding domains, and water has a molecular geometry called bent because it has 2 lone pairs and 2 bonding domains. You don't have to worry about these molecular geometries for this class. We only care about the fact that all of these examples have tetrahedral electron geometry around the central atom. In this example, formaldehyde, we have 3 electron domains around the central atom. It's called trigonal planar. The angle between any of the bonds is 120 degrees. Ozone is another example where there are 3 domains around the central atom. Therefore, it also has trigonal planar electron domain geometry. The last one to remember is if there are 2 electron domains, as in CO2. This is called linear, and the angle between the bonds is 180 degrees. So there are only 4 geometries that you need to remember: linear, trigonal planar, and tetrahedral. In organic chemistry, we're often looking at more complex examples. We want to be able to assign the geometry and bond angles around each atom other than hydrogen in a molecule. Let's take a look at an example. Let's start from the left. This C is surrounded by two electron domains, the single bond to H and the triple bond to the other C. So the geometry around the C is linear, and the angle between these two bonds is 180 degrees. Let's move to the next carbon. It also has two electron domains, the triple bond and the single bond to the next carbon. That means that this carbon is linear too. The next carbon has four single bonds. That means it is tetrahedral. The angle between the bonds is 109.5 degrees. Finally, we get to the oxygen. It has two lone pairs and two bonds, so it is tetrahedral also. The bond angle between the CO bond and the OH bond is also close to 109.5 degrees. In general chemistry, you may have talked about how the presence of lone pairs changes the bond angle, but we won't worry about this. We might redraw the structure so that we show the geometry of the molecule slightly more accurately. It would look something like this. Also, remember, you can always build a model to see what this looks like in 3D. Talking about geometry is important because experiments have actually measured bond angles and molecular geometries. Thus, we will use the geometry of a molecule, which can be experimentally determined, to help us determine the hybridization of an atom using valence bond theory.